concerns a mass spectrometer. Mass spectrometer will be taking a look at magnetic and electric force, but the bulk of this will be on the magnetic force. So we have a magnetic force, and in the whole region, outside the device, inside the device, we're going to claim that there's a magnetic field of 0.16 teslas that's directed upward out of the page. So that's the purpose of these circles with a dot at the center, showing that B is upward out of the page. Somehow we take one electron off of atoms. We have singly ionized atoms, so they're going to be carrying a positive charge. So our atom is here, and we somehow, don't care how for this problem, we launch that atom off to the right through this region where there's a magnetic field. 0.16 teslas, again pointed upward. What we desire is that out here where there's an entrance slit for the mass spectrometer, we'll continue to have magnetic field in here, but it goes through this entrance slit. We want these to go, want certain atoms to go through in a straight line through the entrance slit. Only atoms that have a speed of 8 times 10 to the 4th meters per second do we want to have travel on a straight line outside of the main body of the mass spectrometer. Well, how do we accomplish that? The magnetic force, if we have a positive particle, and if I put my fingers first in the direction of the velocity and then rotate my wrist such that my palm faces the magnetic field, and I can easily turn my fingers into the direction of the magnetic field, that will give me the direction of the magnetic force. So if we do that here, my fingers would go off to the right in the direction of the velocity, and then I would, I don't know if I can do this from where I'm sitting, my fingers will go off to the right, go into upward for the direction of the magnetic field. So there is a magnetic force in here down the page. Magnetic force direction is down the page. This is not going to lead to straight line motion if there's only one force. Well, let's create a second force by applying an electric field only out here, no electric field inside the body of the mass spectrometer, but outside we have an electric field present. What will I need for the direction of the magnetic field? Well, for the for the electric field, what do I need for the direction of the electric field? The force created by the electric field is the charge multiplied by the electric field. So what do I need for the direction of the electric field? Here we get the direction from right-hand rule, so I won't put an arrow denoting a vector there. Well, we're dealing with a positive charge, an ionized atom that carries net positive charge, though the electric force and the electric field are going to be in the same direction. We need an electric force to balance the magnetic force. So we need up towards the top of the page, and that will be the direction of the electric field. The electric field will be up the page. So we will take care of that and balance these two forces. So the magnetic force and the electric force have to balance each other. So the net force will be 0. The magnetic force is going to be QVB. The velocity here is perpendicular to the magnetic field, so the sine theta factor will have a value of 1, so I'm not going to copy it down here. The electric force is Q times E, and it turns out that the charge is not important. What's important is to have the magnetic field coming up out of the page, the electric field up the flat in the horizontal page that I have here in front of the camera. So that is our situation, and the electric field we need is simply the speed of this atom that we want times the magnetic field that we have. So we have those numbers, so let's go ahead and substitute them in. We've got 8 times 10 to the 4th meters per second. That's our desired speed. We're using a magnetic field of 0.16 teslas. A little bit large, but hypothetical situation. We multiply those two together and we come up with 1.28 times 10 to the 4th volts per meter. We're using standard metric units of meters per second and Teslas. So when we multiply those together, we get standard metric units for the electric field, volts per meter. 1.28 times 10 to the 4th volts per meter, directed up the page. So I want to put an electric field on here, same direction as the electric force. Okay, now those atoms move through the slit. They go inside the mass spectrometer. We're going to take the electric field to be 0 there. We still have the same magnetic field strength. And they're going to move, these atoms now will move in a circle. They're going to feel a magnetic force still down the page, and they're going to have a circular path. Now, as the velocity changes direction, the magnetic force will change the direction. The magnetic force is always perpendicular to the velocity. So just, this may not be to scale, but the atoms are going to come around here in a semicircle and hit the wall of the mass spectrometer. And what we want to calculate now is the mass of the atom, given that this distance x, on how far away from the slit the atoms hit the wall, that's 12.5 centimeters. We want to use that to somehow calculate the mass of the atom. Well, in this problem, the magnetic force is creating the centripetal force. And we calculate the magnetic force with QVB. The sine theta factor is a 1 because the velocity is perpendicular to the magnetic field. And we have the centripetal force, mv squared over r. So one factor of the velocity will cancel on each side. And we want to calculate the mass, so I'm going to divide both sides by the velocity, or the speed, really, and multiply both sides by the radius. So when I do that, I find that we can calculate the mass. We're multiplying both sides by r, so we'd have QBr, and we're dividing both sides by the speed, the v symbol. So there's our equation, or our source of calculation for the mass. And we have the numbers. We can look them up. We have a singly ionized atom. So that's carrying just the fundamental unit of charge, plus 1.6 times 10 to the minus 19 coulombs. This atom has one more proton than electrons, in the count of electrons. So there's a slight imbalance in the charge. There's one proton that's not paired off with electrons charge-wise in the atom. So we have that value for the charge of the object. We have a magnetic field of 0.16 Teslas. And we have a radius of some value. Do you think it's 12.5 centimeters? Again, we're told that we have the entrance slit here. The object hits the wall. Distance x is 12.5 centimeters. That's diameter. And it's not in standard metric units. It's in centimeters rather than meters. So we have to do two things. We have to make this 0.125 meters of diameter, and then we have to divide by 2. So when we take those facts into account, I get 6.25 10 to the minus 2 meters. So we must use standard metric units here to get kilograms back here. And then we have the speed. Our velocity selector out in front of the mass spectrometer has allowed only atoms that have a speed of 8 times 10 to the 4th meters per second to go straight through into the mass spectrometer. So put that into your calculator, and hopefully you'll come up with 2 times 10 to the minus 26 kilograms. That's a reasonable number for an atom, because a proton is 10 to the minus 27 kilograms, roughly. So we have a solution here that makes sense. Can we make some educated guess about the name of the element? We have the mass of one atom, 2 times 10 to the minus 26 kilograms, in the mv squared over r. One object going around the circle is the m, mass of the object moving in the circle. Well, let's do a little conversion down here. Let's do 2 times 10 to the minus 26 kilograms. And I'm going to multiply by 6.022 times 10 to the 23rd atoms per mole. And I'm just going to do the per mole here. And what this works out to be is that if you multiply these two numbers together, 0.012 kilograms per mole, or if I change it to grams, I have to move 3 places, we would have 12 grams per mole. Can you think of some element that has 12 grams per mole? It has an atomic mass number of 12. And perhaps you remember carbon and the isotope that has 6 neutrons along with the 6 protons of carbon. So carbon 12, different notations you can use to write that. But that would be one choice. There are other choices, other isotopes of atoms that aren't carbon, but I won't get into that. So there we have the mass spectrometer. The two key parts. Outside the slit, there's a velocity selector using a balance of electric and magnetic force, and there's only a balance for a certain speed. Once you have a certain electric field and a certain magnetic field, these forces only balance for a certain speed. Objects that are going too fast, they have more magnetic force, they curve one way. Objects that are moving too slow, the electric force dominates, they curve the other way. Once we get inside the mass spectrometer, then the magnetic force supplies a centripetal force. We solved this equation for the mass of the object and worked out the mass of an individual atom. Then we use Avogadro's number to inform us how many grams per mole for this particular object. So keep practicing with that. Ask your instructor some questions.